We're surrounded by numbers all day, every day. But have you ever stopped to think about what they really are? It turns out they have this deep, hidden structure, a kind of secret code that governs everything.
So what if I told you that every single number you've ever thought of has its own unchangeable, unique identity, a kind of mathematical DNA? Well, it does. And today, we're going to crack that code.
All right, to get this code, we have to start with the building blocks. I mean, the absolute fundamental atoms of the number world. So let's just grab a big, kind of random-looking number. How about 32,760? Right now, it doesn't look like much, but we're about to perform a little mathematical surgery to see what's really inside. Okay, the first thing you notice, right? It's an even number. So we can pull out a 2, simple enough. Now we're left with 16,380. But we are far from done. That's still even, so let's pull out another 2. See what we're doing? We can just keep going, breaking this thing down into smaller and smaller pieces. It's like taking apart a really complex machine, just bolt by bolt. And once we've pulled it completely apart, this is what we get. This is the bedrock, a string of these really special numbers all multiplied together. But look closer. You can't break these numbers down any further. No way. And these special numbers, they have a name. They're called prime numbers. You got to think of them as the atoms of mathematics. They are the indivisible, fundamental particles that all other numbers are built from. 2, 3, 5, 7, 13. These are the Lego bricks of the entire number universe. So we can break numbers down into these atoms. That's pretty cool. But the truly amazing part, the real secret code, is this universal law that governs them. And we have this man to thank for it. Carl Friedrich Gauss. He was an absolute giant in the history of math, and he was the one who actually proved this incredible property of numbers. What he proved is now called the fundamental theorem of arithmetic. And listen, the key point is not just that we can break any number into primes. The part that will blow your mind is that there is only one way to do it. It is unique. This is it. This is the secret code. The prime factorization of a number is its unique fingerprint. The combination of primes 2, 3, and 5 will always make 30, and no other combination of primes in the universe will ever get you there. That uniqueness is everything. Now, you might be thinking, okay, that's a neat abstract idea, but what's it actually good for? Well, this theorem is also an incredibly powerful and practical tool. Let's see how this secret code actually builds something useful. Remember trying to find the highest common factor back in school? Well, the fundamental theorem makes it just ridiculously simple. Let's take two numbers, 96 and 404. Step 1, we just find the unique prime fingerprint for each one. So we break them down into their prime atoms. To find the highest common factor, all you have to do is see what they share. So you look at their fingerprints. You can see they both have 2 2s. We just multiply those shared factors together, and that's it. The HCF is 4. It's simple, it's elegant, and it's all thanks to this unique code. But this theorem does way more than just help with homework problems. It actually lets us prove some of the most profound and, frankly, some of the weirdest truths in all of mathematics. Let's talk about irrational numbers for a second. Numbers like the square root of 2. Their decimals just go on forever with no pattern. You can't pin them down as a neat little fraction. But how can we be absolutely 100% sure of that? We use this beautifully clever technique called proof by contradiction. It's kind of like playing detective. We're going to start by assuming the exact opposite of what we want to prove. We'll just pretend for a moment that the square root of 2 is a perfectly normal fraction, and then we'll see if that idea leads us somewhere completely ridiculous. Okay, so here's our starting point. We're going to assume the square root of 2 is equal to some fraction a over b. And this is the most important rule of our investigation. We're going to insist that this fraction is in its simplest possible form. That means a and b share absolutely no common factors. Got it? Good. Now, for a little algebra, if we square both sides of that equation and just move things around a bit, we get this. 2 times b squared equals a squared. Now stop and look closely. This tells us something huge. It means a squared has to be an even number, right? Because it's equal to 2 times something. And here's another cool little logical leap. If a number squared is even, then the number itself must be even. Think about it. An odd number times an odd number is always odd. So A has to be even. And if A is an even number, we can just say it's 2 times some other number. We'll call it C. So let's take this new identity for A and plug it back into our earlier equation. When you simplify it all down, you discover something that should make the hairs on your arm stand up. You find out that B squared must also be an even number. And if B squared is even, then B itself has to be even.
And, hang on a minute, do you remember our number one rule? The whole investigation started because we assumed that A and B had no common factors. But all our logical detective work has just proven that they are both even, which means they have to share a common factor of 2. Our assumption has led to a complete, total contradiction. It's nonsense. It's impossible.
That contradiction, that is the proof. The only possible reason we ended up in this logical paradox is because our very first assumption, that the square root of 2 could ever be a fraction, was dead wrong from the start. So let's just quickly recap what we figured out. Every single number is built from primes in one and only one unique way. This prime fingerprint isn't just a party trick, it's a foundational law of the universe. It gives us practical tools, and it lets us prove these incredibly deep and strange truths about the very nature of numbers.
The fundamental theorem of arithmetic is just a perfect example of a simple, beautiful rule hiding right under our noses, but with these massive consequences. It really makes you wonder, doesn't it? What other secret codes are out there, woven into the fabric of our world, just waiting for us to find them?